So only 36% of students got this question right. Are you in the top 36% of GCSE Physics students? Well, have a go at this question and you'll soon find out. We got this question as question 2 on last year's paper. In fact, this is actually the June 2023 paper. Figure 2 shows the equipment a student used to determine the specific heat capacity of iron. So you can see immediately it's probably going to be a question about this experiment that they've set up, and they've listed a nice diagram for you. A very common type of question. They're going to list a diagram for you. It's actually more of a picture of an experiment. This won't be one of the experiments typically that you're going to be expected to do. It won't be one of the required practicals. It will just be a different experiment, but it's testing the same skills that you would need to use in those required practicals, okay? So while they might not test you on the required practical directly, they're going to be testing you on those skills, okay? So let's do this question. The iron block the student used has 2 holes, one for the heater and one for the thermometer. So they're basically trying to work out the specific heat capacity of iron. So this is the iron block that they're heating up. Before the power supply was switched on, the thermometer was used to measure the temperature of the block. Okay, so this is a skill they're actually testing. It's about the thermometer being used to measure the temperature of the block. The student left the thermometer in the iron block for a few minutes before recording the initial temperature. Suggest why. Okay, so for 1 mark, what would you say? I'll give you a second. Okay, so the first thing we're going to notice here is it's a suggest question. Okay, so that means that typically the exact answer, you wouldn't be expected to memorize it or know it off the top of your head, but you just need to make a sensible suggestion using the principles that you've been taught in this course. Okay, so hopefully you know the principles, right? So the principle they're really testing is how do you use a thermometer to measure temperature. Okay, so that's the thing that's highlighted there. Now, why would you need to wait a few minutes before recording the initial temperature? Well, the whole idea is that you want the temperature of the thermometer to be equal or the same as the temperature of the iron block. Okay, so that's really the key here. That's what they're testing is, practically speaking, if you had to take the temperature of something, why do you need to wait a few minutes or at least a few seconds when you actually insert the thermometer into the substance, okay? The idea is that the thermometer itself is not going to instantly reach the temperature of whatever you're trying to measure, okay? You need to wait for that thermometer to reach the same temperature of whatever it is you're trying to measure. That's when you take the reading, okay? So obviously if you imagine you're taking the temperature of someone who's ill, you put the thermometer in their mouth, you don't take it out straight away, you leave it in there for a few seconds and you wait for it to reach the temperature of their mouth before you actually take the reading, okay? So it's a bit of a common sense question, but it's not one that all the students got right, okay? So you need to understand what's going on when you actually use a thermometer to measure temperature, okay? The key here is that you need to refer to the iron block's temperature rather than room temperature. A lot of students, they would mention things about the room temperature. The thermometer itself, you're not trying to measure the room temperature. Now, because the iron block is in the room, yes, the iron block would be room temperature, okay? Now that's a given, that's fine, but however, it's kind of a bit of a red herring. You're going down the wrong lane, really, if you're talking about room temperature. Yes, the iron block will be room temperature, but what are you trying to measure? You're trying to measure the temperature of the block. So why do you even mention that it's room temperature in the first place? Okay, so you don't really need to even mention room temperature here, right? The key thing they're looking for you to mention is you need to be talking about the temperature of the iron block itself, okay? And that the thermometer is trying to measure that. And essentially, in the AQA spec, they have a specific point that they want to use appropriate apparatus to make and record measurements of mass, time, and temperature, okay? So these are the key ones that you need to know about: mass, time, and temperature. You need to know the theory behind how to measure all of these different quantities and from a practical perspective what that looks like, okay? And so that's the same for all of them, and so you could get very similar questions for all of these ones. So do make sure you are aware of these and you practice these kinds of questions. Pay attention to experiments where you do measure these 3 things, okay? Which is pretty much all your required experiments. If you have done all the required practicals, then you should have covered this in a good amount of detail. You just need to make sure you can recall it for your exam, okay? Okay, next question, we've got an electricity question. It's the one that a lot of students tend to get wrong. So we've got figure 4 shows an electrical circuit used to heat the windscreen of a car. Each resistor in the circuit represents a heating element. The 12-volt battery supplies direct potential difference. What is meant by direct potential difference? So again, it's just a 1 marker, but it is one that students really struggle with, just like the one before. So go ahead. What would you say for 1 mark? All you have to do is define direct potential difference. Okay, so before I give you the answer, I will let you know that just 11% of students could answer this one correctly. So about 1 in 10 people watching this video is going to answer this correctly. There are other 9 of you, I'm sorry to say, you haven't got this one correct. So let's see, are you the 1 in 10? The answer here is actually that the difference, the polarity of the potential difference stays the same. Okay, so how many of you guys said that? The key points you need to mention for this mark is you're talking about polarity and you're talking about potential difference. Okay, so why did only 11% of students actually get that one right? Well, a lot of students, instead of talking about potential difference, which it specifically says in the question, direct potential difference, that's the thing you need to answer. A lot of students talked about charge flow and current. Okay, potential difference is not the same thing as charge flow and current. Potential difference also doesn't flow. So a lot of people will say you might have alternating current or and compare it to direct current. Now, direct current is not actually in the specification for AQA itself, but it is very similar in principle to direct potential difference. Okay, so a lot of students will be familiar with this graph. So essentially, we're drawing a graph of direct versus alternating potential difference. And when we talk about mains electricity, this graph gets drawn a lot. And so this would basically represent alternating current, or if instead on the y-axis, if you label it and we say this is potential difference, this is actually alternating potential difference. Okay, so the idea is, again, you have a positive section and a negative section. The polarity is changing. When you have direct current or direct potential difference, it just looks like that. Potentially, the idea is the polarity will stay the same. You will never switch from positive to negative polarity or vice versa. Okay, so that's what direct potential difference means. And I think most of you watching will probably be familiar with this kind of graph. And if I asked you to draw direct potential difference on a graph, I think a lot of people would be able to draw this. Same with alternating potential difference. But you do need to be aware of how to explain this in words. Potential difference is not the same as current. So when we draw a circuit, we might draw a cell like this and a resistor like this. And we can talk about the direction of the current, right? So the current might flow this way and then this way if it's alternating current. But the idea is with potential difference doesn't flow, right? It's not actually going around the circuit. What's going around the circuit is the charge or the current. And so when we talk about potential difference, we're just talking about the polarity over here, that these might switch around. Okay, now generally with a cell, the potential difference is going to be fixed, but you can also have alternating potential different sources as well. Okay, so really the key thing here is what changes when you have alternating potential difference. It is actually the polarity or the direction. You don't want to confuse it with things like charge or current. And remember, to answer the question, it sounds really basic, but it does say in the question potential difference, so don't start talking about charge or current. Okay, the next question we're going to be looking at was all about trends in energy usage. So this is one of the last parts of the specification when you look at energy. And so let's get into this question. 4.3 figure 5 shows how the power output of the generator varied during 1 year. And you can see they're basically giving you this nice graph with the years, the months on the x-axis, and the power output on the y-axis. A solar power system is installed in the remote village in addition to the hydroelectric generator. So what you're seeing over here is the power output of a hydroelectric generator. Okay, so let's write that down. So this part is mentioned earlier in the question, but we just need to understand the context. Explain why this improves the reliability of the electricity supply to the village. Use information from figure 5. Okay, so it's giving you this prompt here, and this is worth 2 marks. So what would you say for 2 marks having read that question? If you get 2 marks here, you're actually part of the 6% of students that actually got 2 marks on this question when it was in the exam paper. 33% of students managed to get 1 mark. So what do you actually need to say for the marks? Okay, the first thing that you need to mention is that the power output from the hydroelectric generator would be lower in the summer, but that same power output of this time, not the hydroelectric generator, because what did you add? You added the solar power system instead, right? So the same power output of solar would be higher. Okay, so that's basically when you compare the two, that would get you 1 mark, right? That the hydroelectric generator would be lower in the summer, whereas the solar energy would be higher, and you can even say vice versa. And then therefore, based on that, this increases the reliability. Why? You need to say specifically that there's less variation in the power output. Okay, so let's see how that would work in terms of our graph. So you can see over here, you've got the graph of the hydroelectric generator. So what you'd expect to see if you were to draw a similar line for the solar power is in the winter months, you'd have quite low solar energy. Then it would go up during the summer months, and then decrease back down as you get away from the summer back into winter. Okay, so you'd see basically the opposite trend. And the idea is then if you average these two out, what you'd get is quite a stable graph of energy, right? So if you were to add these up at every point, then your energy output will look something like this, right? You get a nice kind of straight line with a high power output, and you don't get this big dip in the middle. That's the thing that you're avoiding, okay? And that is what makes it more reliable. So that's essentially what's going on, and you just need the ability to explain that in words. So a lot of students really struggled putting that together, okay? And so what some of the common mistakes that we had was that you lack this comparison statement, okay? So over here, we can see we compared solar power to the hydroelectric power. You do need to be able to understand the differences between different ways of generating energy and the advantages and disadvantages and when some might be preferred to others, okay? So in this case, they've given you this graph. The thing you should notice from this graph straight away is this big dip, okay? Because remember, they're talking about reliability in the question. So this big dip is showing you that the power output is not reliable. So how would solar power actually counteract that dip? That should be your line of thinking. So you almost need to go a little bit backwards in terms of this question. How would solar power actually fix this dip? Well, what do you want to do? You want to have less variation in power output. How does solar power result in that? This is the first part, okay? So this would be 1 mark. This would be the second mark. Another common mistake a lot of students made, that on the second mark, they just said, oh, it's more reliable, okay? Now, this is not enough for the second mark because it actually tells you it improves the reliability. This is given to you in the question, so you can't just get a mark for repeating what is in the question. You need to go a level below that, and you need to say why it's more reliable. Well, the reason why it's more reliable is because there's less variation, okay? And just like we showed in the graph, you want a nice straight line, and so you have less variation when you add this additional power source, okay? So it's all about total power output, okay? So again, it's trends in energy usage, or in this case energy generation, and you need to understand how to answer questions based on these kinds of graphs, okay? And it won't be the same graph every time, so you just need to understand generally what are the important things when we look at generating electricity. It's about reliability, it's about how much energy we can produce, and also at what times you can produce that energy. Because sometimes if it's really sunny, you can produce lots of energy, you're thinking it's great. But if you want to make a fair assessment, you also need to look at what times of the year, what times of the day you can actually produce this energy, because you need to be thinking about demand as well when you want to use it, okay? So these are the kind of things hopefully you should have covered, and those kind of principles will help guide you on these kinds of questions. Okay, next we're looking at a radiation question. So table 1 gives some half-life of some other radioactive isotopes. So you can see we've got 4 different isotopes listed and the half-lives for each of them there. 5.3 is not actually the question that a lot of students struggle with, but we'll just read it. A sample of fluorine-17 has an activity that is 1/4 of its original activity. Calculate the age of the sample of fluorine. So I'll leave that one for you guys to complete. It's not one that a lot of students got wrong, so we won't cover it in this one. But this next question, 5.4, all of the isotopes in table 1 emit beta radiation. Explain which isotope would cause the biggest risk to a person's health based only on the half-life of each isotope. Okay, so which one of these will be the biggest risk? It's 3 marks. Here's the table. I'll give you guys a second. What would you say for 3 marks? Okay, so which one, first of the 3 marks, you need to actually say which one is the correct one in terms of which one would be the biggest risk to a person's health. Okay, so this is the options. So if you said fluorine-18, that was by far and away the most common choice, but it was the wrong one, okay? The correct answer here is nitrogen-18, right? So most students did choose fluorine-18 based on the fact that it had the longest half-life. So if you did the same, you're not alone, but it's not actually the correct answer, okay? Nitrogen-18 is correct. Less than 1% of students actually got all 3 marks here, and actually only 15% got even 1 mark over here, okay? So to say that they only 15% picked even this nitrogen-18 over here. So instinctively, you might say the one with the longest half-life is going to be the most dangerous because it takes the longest to decay, okay? So the idea is this would have a high amount of radioactive nuclei for a longer period of time, okay? Now that is correct, and over a long enough period of time, the one with the longer half-life will tend to produce more radiation. However, in this case, we're actually looking at which one will emit the radiation at the highest rate, okay? So we're looking at the rate of radiation. And hopefully those of you who have done your revision will know immediately when I say rate of radiation, you should be thinking activity, okay? Activity is the rate of radiation. Now, radiation itself is actually this beta particle, okay? It's a beta radiation. That means it emits these beta particles, and this is the radiation. So whenever you emit this beta particle, that is what's actually contributing to the activity, right? So how often are you going to be emitting this beta particles? The more amounts of decay you have, or the frequency of the decay, is what actually drives this activity and what makes things more dangerous. So over here you can see basically nitrogen 18 by far and away has the shortest half-life. That means it's going to be decaying at the fastest rate. That means it's producing the most amount of radiation per second. It's going to have the highest activity, okay? So if we look on a graph, easiest way to explain this is with a graph. And over here, you're going to have the number of nuclei, and you're going to have time on the x-axis. And the idea is when you have something with a really long half-life, then this number of nuclei will tend to stay quite high for a longer period of time. Now, when you have something with a really short half-life, this is going to drop a lot faster. But what that does mean is that this nuclei, all of these radioactive nuclei, is decaying much quicker and giving off this beta radiation much quicker. Remember, how do you get this beta radiation in the first place? How do you get this radiation particle? Well, you have a neutron decaying into a proton plus an electron, and this electron is your beta particle basically, right? So every time this happens, that's when you emit your radiation. Therefore, the more frequently this happens, that means you're going to have a high activity. That's going to be what's going to be more dangerous, because your beta particle is going to be emitted. You're going to emit more of them in a shorter space of time, okay? And the idea is then, for 3 marks, how would you structure this answer? Well, first thing is you want to say is nitrogen 18. That would be your 1 mark. That is the correct answer. Then you want to say, why is it nitrogen 18? Well, it has the greatest activity, okay, for the reasons we just explained before. And therefore, why is that dangerous? Well, remember, when you talk about the radiation danger to a person, you always want to talk about radiation dosage, okay? So the radiation dosage that the person experiences will be the highest. You could also say the amount of radiation that's absorbed. That would also be fine, but you're going to have higher radiation dosage or radiation absorbed. You can even say here it's going to be per second, okay? But the idea is that if you expose each of these isotopes to the person for the same amount of time, and we're going to assume it's the same amount of time because it's asked us to base it only on the half-life, right? So we can assume that every other factor is the same, and therefore just based on the half-life, nitrogen 18 will have the highest activity, and therefore it will actually produce and emit the most radiation. And because it's the same type of radiation, it's all beta radiation, it's the same danger, okay? So it poses the same risk. In this case, basically one just produces more than the others, and therefore that one is the most dangerous, okay? So we don't want to get confused. We're not comparing isotopes at different points in their life. We're comparing different isotopes with different half-lives, okay? And remember, the key thing when it comes to human, we can always quantify the risk. So that's why we talk about radiation dosage. And remember, what actually is radiation? If you understand what radiation is, this question becomes a lot easier. Radiation itself is these particles that we produce, right? It's these beta particle, that's radiation, or the gamma ray particle, that's also radiation, or the alpha particle. This is your radiation. So the more of this you produce, that's where the danger is, okay? So, and these are only produced when you have decay, and the higher that rate of decay, that means your activity is also going to be higher, okay? So those are the key things you need to know on this one. The faster the rate of decay, the more the radiation dose. If you understand your key fundamentals about nuclear radiation, this question does become a lot easier, but we don't want to get tripped up with the half-lives point, okay? Remember, these half-lives is not necessarily the one that has the longest half-life, which is the most dangerous. You do need to also be thinking about the type of radiation and the amount of decay per second, the decays per second, or the count rate, okay? Okay, the last one we'll do is actually the next part of that question. 5.5, people who work in the nuclear power industry need to be aware of irradiation and contamination. Describe the difference between irradiation and contamination. Now, this is worth 2 marks. And actually, if you've done your revision and you've revised your definitions, this one should be really simple for you. And actually, if I tell you that only 18% of students got 2 marks here, I think a lot of you would be surprised, okay? Because actually, if you've done your revision, this should be very simple. So for 2 marks, what would you say? Okay, so it is a term that students do get confused about a lot, but if you read through your specification, they do actually define both of these for you very clearly, and hopefully they do make sense, right? So irradiation, what is irradiation? Essentially, irradiation is just when you expose an object or a person to radiation, right? So that's your first definition for 1 mark. Then, okay, how do we define contamination? So hopefully contamination is a little bit simpler because you can get different types of contamination. So you should be familiar with it in different contexts. So contamination, very simply, is just where you have unwanted radioactive material on a person or object. Okay, so normally some kind of non-radioactive person or object, okay? So those are your two definitions. Those, if you wrote that down, that would definitely be enough to get you the 2 marks. So what are the common pitfalls here? Well, essentially, as long as you understand radiation, this should be really simple, okay? Irradiation is just when you expose something to radiation. So what is radiation? Well, we spoke about it before. Your alpha particles, your beta particles, or your gamma rays. This is what we call radiation. I want you to make that link, okay? When someone says radiation, you should be thinking alpha, beta, or gamma particles, okay? That is what radiation is. When you're exposed to these particles, you're exposed to radiation. That's what we're saying, okay? So that is what irradiation is. As long as you understand that, you should be absolutely fine defining radiation, right? That's the first thing. Contamination is pretty common sense. Something is where it shouldn't be, okay? So in this case, you're not talking about the radiation itself. So we're not talking about beta, gamma, or alpha. We're talking about the radioactive material. So how do we define radioactive material? It's anything that emits alpha, beta, or gamma. So that's it. This is really as simple as it gets, okay? So anything that decays is a radioactive material. When it decays, it produces radiation. That's the alpha, beta, gamma rays, okay? So that's really it. But it's really important you understand those definitions that we just went through. A lot of students get really confused about this, but when you simplify it down like that, it's dead simple. It makes these kinds of questions really easy. Make sure you've done your revision, you've gone through your flashcards, whatever, and you know the definitions when it comes particularly to nuclear energy and decay, things like that, okay? It's one that trips people up, but actually you can see this is a really easy 2 marks once you actually know what you're doing, okay? So we'll leave it there. Hopefully this video was useful, and I'll see you guys in the next one, and good luck with all your exams.